This is the second pre-flight on atomic nuclear physics. The basis of this is how nuclear reactions produce energy. On this particular one, we're going to focus on nuclear fusion, which will be taking two atoms and combining them together to make a bigger atom. Now, the whole idea of how this began is if we took two protons and two neutrons completely isolated from each other and we put them on one side of the scale, and then we took a helium nucleus, which is two protons and two neutrons, we would think they would be balanced. But the truth is, this side actually weighs more. The scale is going to fall down to the left. So by bonding these things together to create this, we actually lose mass. In fact, hydrogen 2 has an atomic mass of 2.0158, and it would take two hydrogen 2s to make a helium 4. But you can see the atomic mass of hydrogen 2, two of them that is, two hydrogen 2s, is greater than the atomic mass of helium 4. So, let's go ahead and see how much energy would be released in a reaction like that. Einstein came up with the equation E equals mc squared, or the energy released equals the mass times the speed of light squared. Well, what mass are we specifically talking about? Whoops. The mass we care about is the difference between the two hydrogens and the helium. So we'll do final minus initial. And the resulting mass is a loss of 0.29. Sorry, 0.029. Now that's atomic mass units. And if you take a look at your table of information, the unified atomic mass unit does convert into kilograms. It's 1.66 times 10 to the negative 27th kilograms. So we come back here, in order to get that mass into kilograms, which we can use in E equals mc squared, the mass is 0.029 times 1.66 E negative 27. And we go here, multiply it by 1.66 times 10 to the negative 27, and we'll get an atrociously small number. And you know what? I'm going to use a Google calculator because I don't like that. (4.81 E negative 29). We take that, multiply it by the speed of light. So we'll take our 4.814 E negative 29. And multiply it by c squared. Or 9e16. it's 4.33 E negative 12 joules. Now this may seem like a very small amount of energy released in one reaction, and for one reaction it is very small. But here's the thing. If I were to take 1 kilogram of hydrogen and convert it into approximately 1 kilogram of helium, what I'm noticing is I am losing this percentage of the weight, which is a decent amount of percentage over 1 kilogram. Just 1 kilogram of hydrogen is going to produce enough energy to power my house for arguably the rest of my life. It's enough to power a city for a couple of days. So one atom itself releases a very small amount of energy, but we're not going to do a reaction with one atom. We're going to do a reaction with, an insane amount of numbers of atoms, e to the 25, e to the 26, e to the 27. So the idea of this pre-flight is in nuclear fusion, and this does work for fission too. What we find out is as the atoms split in the higher levels, their mass decreases as well. But here, because the mass of these 4 particles separate is actually more than combined in the helium, it means we lost energy. So H2 had a mass of 4.0316, H4 had a mass of 4.00260. We use E equals mc squared, taking the difference in the masses, multiplying by the speed of light. We can then figure out, the difference in the masses multiplied by the speed of light, we can figure out the energy. Before we did that though, we took the atomic mass unit of 0.029, multiplied it by this conversion factor here to get the mass in kilograms. Well, that's all I have, so thank you for watching.